Hope everybody's having a good day so far. Probably had a great night of sleep. I would estimate you slept maybe 8-9 hours. It's the standard amount. It's nice talking to you guys too. All right, cool. So let's go ahead and start off with our second question here. So from that same file that I sent out on Friday, we went through and did this part about the office workers arriving to the building. We had a table. We did a bunch of stuff with it. Wonderful, wonderful, wonderful. All right, so now we're moving on to the second question. So again, it's kind of a longer question, multiple parts. And so let's just go through. All right, function f is twice differentiable for x greater than or equal to -6. A portion of the graph of f is given in the figure above. The areas formed by the bounded region between the graph are labeled. Let g be defined. Okay, so I have a separate function g that's based on f. So that's interesting. And note, if you're ever given a graph in the AP test, pay close attention to what is this actually a graph of. Okay, because you might get confused about what you're actually looking at. But this is a graph of f. Right? I assume this question is going to, like this part A asks about a limit and G, but for the rest of the parts of the questions, I assume it's going to ask me stuff about G specifically. Do not rely only on the graph. Okay, now F is used to build G, so we'll use it in some ways, but this is not a graph of G. Okay, so just have that clear in your mind whenever you're doing a problem if you're given the graph of it, of what am I actually looking at. All right, so the first thing that we want is find the limit as x approaches -2 of this crazy expression here. Right, g of 2x minus 4x all over e to the x squared minus 4 plus x plus 1. Okay, interesting. So let me first consider the numerator. If it were a more simple expression, I might just try to do it all at once, but since it's kind of a complicated expression in the top and bottom, let me just consider them each individually for a second. So g of 2x minus 4x. So I'll go ahead and just copy that down. G of 2x minus 4x. The first thing that we try to do with the limit is just plug in the value. So let's plug in -2. So that would equal g of -4, right? 2 times -2, -4. Minus 4 times -2. So -4 times -2, that would make plus 8. All right, now what is g of -4? So g of -4, so let's use our expression. G is the integral from 2 to x, but in our case 2 to -4. F of t dt, and then plus 8. Now there's kind of some trippy business here with the bounds. Notice that the lowest value is the lower bound, and the higher value is, and I said that backwards. The higher bound is actually the lower bound, right? +2 is greater than -4. So remember, we can actually, let's switch this, but we have to introduce a negative sign. we can always switch the bounds, the upper bound and the lower bound, doesn't matter, but if we do switch them, it will introduce, it'll introduce this negative sign here. Okay, so the integral of f from -4 to +2. Well, what is that? We have a graph here. So from -4 to +2, we have this upper area, which is 10. We have this lower area, which is 2. So the total area from -4 to +2 would be 8. Because remember, any area that's below the x-axis represents a negative area. So +10 plus -2 is 8. So we have -8 plus 8. Remember, because this negative was out in front here. Well, -8 plus 8, I believe, is 0. All right, so that's interesting. That makes me wonder if I'm going to get 0 whenever I do this bottom limit as well. All right, let's see. The limit as x approaches -2 of e to the x squared minus 4 plus x plus 1. So again, first thing we try to do is just plug in 0. Or sorry, not plug in 0, but plug in -2. So -2 squared is 4, so 4 minus 4 is 0. E to the power of 0 is 1. So 1 plus -2 plus 1. Yep. That also equals 0. So overall, this limit, if I just evaluate it straight up, I get 0 over 0. Damn. All right. Well, we know if we get 0 over 0, or if we get infinity over infinity, we use L'Hopital's rule. Okay, so let's try to take the derivative of the top, derivative of the bottom, and see if that helps us out. Just let me scroll down here some more. So let me put a little note to myself. Use L'Hopital's rule. So the derivative of the numerator. So the derivative of g is g prime. But then I would have chain rule because the inside is 2x. So 2 times g prime of 2x. And then minus 4x, so the derivative would just be minus 4. All right, so remember this 2 comes from using the chain rule. And then denominator, I'm also going to have to use the chain rule. So the derivative of e is just e. So I'd still just get e to the, oops, let me write that better. Right. E to the x squared minus 4. But then chain rule, so what's now the derivative of this exponent? 2x. So 2x e to the power of x squared minus 4. Derivative of x is 1. The derivative of this 1 is 0. So it's just this plus 1. Okay, so just looking at this, I don't know, I think this will turn out a little bit better for us, but let's see. Who knows? We might have to use L'Hopital's rule again. There's really no way of knowing immediately. All right, so let's just try to plug in -2. So 2 times g prime of 2 to -4. Not, oops, sorry, I forgot the g part. Inception. Okay, yeah, maybe. So 2g prime of -4 minus 4 over 2 times -2, so that would be -4 e. -2 squared is 4, 4 minus 4 is 0. Oh yeah, so we already decided if I plug in -2 to that e exponent, I just get e to the 0th, so that's 1. So this would just be negative 4 plus 1 in the denominator. So that's promising that my denominator is not 0. I really like that, because even if the top is 0, great. Well, that just means it's 0. If the denominator is 0, I'm worried, because either I'm going to get 0 over 0 or my denominator is 0, which is impossible anyways. So I'm really encouraged that my denominator is definitely not going to be 0. It makes me think I'm doing something right for once in my life. Okay. Really now I just need to figure out what is g prime of negative 4. Well, hold on. Let's go back up here. If g of x is this function, then g prime of x is just equal to f. Right, now technically that's the second fundamental theorem of calculus. If we take the derivative of an integral, so remember we do the function times the derivative of the upper bound, so that's times 1, minus the function, plug in the lower bound, times the derivative of the lower bound, so but this derivative of 2 is 0. So all this is garbage because it's just 0 times 1. We don't need to write times 1, so it's basically just f of x. All right, second fundamental theorem of calculus. All right, so g prime is the same as f. That's good to know. So I need to know, so basically this is just what is f of negative 4. Negative 4 plus 1 is negative 3 in the denominator. So f of negative 4, well, let me go to my graph. Maybe this will help. Aha! F of negative 4 is 0. That's awesome. So 2 times 0 is 0, minus 4. So minus 4 over minus 3. My slope is 4/3. Awesome. Wait, did I say slope? My limit? My limit is 4/3. I don't know what I said before. I don't think I said limit. Okay, so this is an idea that we're very familiar with. Getting 0 over 0 for a limit instead than using L'Hopital's rule. The only difference now is this one's just some more complicated functions, but it's okay. All right, part B. Find the absolute maximum of g on the interval -6 to +2. Justify your answer. All right. Absolute maximum on the interval. This makes me think of extreme value theorem, because that's exactly what the extreme value theorem does. Is it tells you there is an extreme value, right? A maximum or a minimum, and a minimum, right? And on a specific interval. Because maybe not every function has an absolute max or an absolute min, but on a continuous interval, there will be an absolute max or an absolute min. So we got to do a couple things here in order to do extreme value theorem. So we have to test the endpoints. So that would be -6 and +2. Maybe that's where the extreme values are, the maxes and the mins. Or, well, and we need to find where the derivative equals 0, and we need to test those points. All right, that's what the extreme value theorem does. Oh no. Oh no. I ruined it. Oh, okay. Okay. So I already know that I have -6 and +2 to test. So let's figure out what else do I need to test. All right. So again, let's figure out where the derivative is 0. So g prime of x, the derivative of g. Well, we already decided from our last problem, the derivative of g is the same thing as f. And as we do in so many cases, we want to set that derivative equal to 0. Okay, so where is f equal to 0? So this is a graph of f. So, and specifically on the interval -6 to +2. So -6, so there's 0, there's 0, there's 0. I already knew that I needed to test 2 because 2 was one of the boundaries, you know, one of the endpoints. So, but whatever. But I definitely need to test also -4 and 0. All right, so let's create a table. Or I guess I should write, so x equals -4, and what was the other one? 0? Yes, -4 and 0. All right, so let's create a table. All right, and I want to test to see which one of these will give me the largest value so that I can find that absolute max. Remember, I'm testing it in g. G prime is what I use to help find where it could be, but to figure out the actual max, I need to use g, the original function. So we're going to test -6 because that's part of the endpoint. That's one of the endpoints. I'm going to test -4 because I found out that's one of the spots where the derivative is 0. I'm going to test 0 because that's also one of those spots. And we're going to test 2 because, well, it's an endpoint and the derivative is 0 at 2. So kind of a double whammy. Okay. So we're just going to plug in these values to our function, right? G, what is g? Well, g is defined by this function, integral from 2 to x of f. So the integral of 2 to -6 f of t dt. I'm going to do the same thing that we did before. Remember, again, these bounds are kind of weird because the smaller number is in the upper bound. So let's switch the bounds, but it'll create a negative in front. That's fine. All right, so that negative. Now, what is the integral from -6 to +2? All right, well, remember, integral represents, or one of the things that we can think about integral as, is the area under the curve from -6 to +2. Okay, great. So from -6 to +2, what is the area under the curve? Well, I've got a 5 down here and a 2 down here. So remember, negative, or area that's beneath the x-axis represents a negative area. So I've got -7 and then +10, because this area of 10 is above the x-axis. All right, so +10, -7, so that would be 3. But we had this negative that we got just from swapping the bounds. So this negative does not come from there actually being a negative area between those two boundaries. But since we swapped the bounds, that's where that negative came from. But the 3 came from doing -5 plus 10 plus -2, right? Just adding up those 3 areas. Okay, so -3. Let me make some lines here to make sure that this is a little easier to read. Okay. -4, so let's do the same thing. 2 to -4, f of t dt. I don't like that that upper bound is a smaller number, so let's switch them and introduce a negative. So I know there's a negative in front, but let's see what the actual, so from -4 to +2, so now from -4 to +2, what is the area between here? Well, I've got a +10 and a -2, since that 2 is below the x-axis, so that would be 8. And again, the area was not -8, but since we switch the bounds, we do have that negative there, so this value is -8 overall. Zero. All right, so from 2 to 0, f of t dt. I don't like, we're going to swap the bounds. So it goes 0 to 2. So the area from 0 to 2. Oh, that area is below the x-axis, so it's -2. But we already have a negative, so that's -2. Which is +2. All right, it's the largest so far because the other ones have just been negative. But let's try this very last one. All right, so the integral from 2 to 2, f of t dt. All right, I don't even need to look at the graph here. Hopefully we remember that if we take an integral and the bounds a and b are the same from 2 to 2, that's 0. Okay, so which one of these is the absolute max? 2, right? -3, -8, 2, or 0. Okay, 2 is the largest number there. So let's put this into a final answer. So, it's ugly. So on the interval -6 to 2, the absolute maximum of G is 2. And I guess we might as well say where it happens. So where does it happen? It happens whenever x is 0. Justify your answer. Okay, so actually let me add in a little bit of justification here. We already talked about what did we use. We used the extreme value theorem. Okay. And since we know that G is twice differentiable, then we know G is continuous. So I'll add on a little bit more here, just to make sure that I get that justification point. So since G is twice differentiable. It is continuous, and we use extreme value theorem. If you're worried about over-justifying, I mean, it's better to over-justify than under-justify, right? Because that's usually like an entire point or maybe even 2 points on a problem. Well, I guess in general. I don't know. Again, this year, who knows? But this is kind of freaking me out again. This is another, no one's really saying anything, but I see that I did click start streaming, so I must be doing something. Guess everyone just dipped out today. Okay. Function f. Oh yeah, we already knew that part. So part C. Definitely streaming. All right. Evaluate the integral from -3 to +1 of x times f prime of 2x. Aha. All right. So immediately when I look at this, I'm seeing that I'm taking the integral of two things that are being multiplied together. All right, so if I were taking the derivative, I would think product rule. Okay, but when I'm thinking of integration, whenever I have two functions that are being multiplied, I'm kind of thinking integration by parts. Right, so integration by parts is this, or no, sorry, not you. Okay. All right. Oh, where'd my cursor go? Hold on. I lost it. Oh, oh, oh. Ah, okay. Hold on. Okay, now I lost my other sheet that I had. What the heck? My other page just disappeared. I need it. Okay, I don't know. Oh, aha. Is that? Oh, okay, good. All right. Just lurking. All right, chill. Okay. All right, what was I saying? Okay, now I got all my stuff back. I'm so tired. Great. Okay, so again, integration by parts. Why did I rate? Okay, so UV, right, minus integral of V du. Okay, so we got to make our decisions here. We got to make choices for U and dV, right? We might make bad choices off the start. V du. That's what I said, right? Did I? This, yeah, V du, right? Is that wrong? We got to make decisions here off the start. Yeah, okay. Okay. Oh, you were answering. I see. Ah, nice. Okay, well, I just didn't know. You were so tired that suddenly you want to answer questions. I was, just thrown back. I set it on time on my end. I guess I'm just behind. Well, again, from whenever I broadcast to whenever it gets put on Twitch, there's like a 5-second delay at least, probably. And then, so besides that, not only is there 5 seconds from when I do it live to when Twitch puts it on the internet, so then you type whatever your answer is, and then, so that's a slight delay, and then an even more delay of when do I actually read the answer, because I can't read, so I have to have text-to-speech, right? I have the Bluetooth piece in my ear that's reading off all your stuff to me. That's right, sponsored by Blue. All right, so let's make some choices. We might have to go back and fix them, but let's just make U this first function, and dv f prime of 2x dx. Right, so I guess more specifically, it would be more accurate to circle this whole thing. So we always start with picking U and dv. We don't start by picking U and v. We start with U for the one choice and then dv for the other choice. Okay, so for du, we take the derivative of both sides, so du dx equals 1. So du equals dx. For this, so we want to figure out what is v. All right, so we're going to integrate both sides. Integral of dv is v. Integral of f prime of 2x. So the antiderivative of f prime is f. But we would need to consider, if we took a derivative, we would have to use chain rule. So the derivative of f of 2x would be f prime of 2x times 2. So we have to account for that. So 1/2 in front. All right, so let's use this formula now. So u times v, so x times 1/2 f of 2x. Right, I did put the 1/2 in front of the x instead of x times 1/2, whatever. Minus the integral of v, so v is this thing. I'm going to go ahead and pull this 1/2 in front, though. Times du. Well, du is the same thing as dx, so dx. And again, we're doing integration by parts. It's windy out there, guys. I think my window almost just smashed in. Okay. And what is this from? This is from -3 to +1. And then this piece as well. No, not the window almost smacked me. I said I feel like the window almost smashed in. Like all of a sudden, you know when it's really windy and like your windows like will start like creaking really hard all of a sudden? That's what mine just did. Luckily I boarded up all my windows weeks ago, so even if they do, the wood will protect me. And since, right, we also have to evaluate this piece from -3 to +1. Right, so if we're doing a definite integral of integration by parts, so this first part we evaluate from 1 to -3, and this integral part we evaluate from -1 or -3 to 1, okay, or whatever the bounds are. The wood will smack you too. Well, no way, the wood's not going to come off. You know how many nails I have in there? At least 3. So, yeah. All right, so let's do this evaluation first. So 1/2, let's plug in 1. F of 2 times 1, so that's f of 1, minus 1/2 times -3. F 2 times -3, so f of -6. All right, minus 1/2. The integral of f from -3 to +1. So remember, integral of f represents area under the curve. Right? So what is the area under the curve? So if I were to plug in 1, f of 2 times 1, well, hold on. Should I do a u substitution? I could. Nah, I'm not gonna actually write it out. But I will write this just to make explicitly clear. This is the area under the curve from, or let's say between, -6 and 2. Now, why -6 and 2? Why not -3 and +1? Because look what's happening inside of f. If I plug in those values, if I plug in -3, I'll get -6. If I plug in 1, I'll get 2. So this represents the area between -6 and +2 of f. Well, let's go back up to my graph. -6 to +2, we've done that area before. We did that in the last part of the question. 5 and 2 represent negative areas, so that's -7. But then this +10, so that represents an area of 3. All right, let's actually get some values. 1/2 times 1 is 1/2. What is f of 1? Well, let's go to our function. Right. Oh, wait. Wait, how did I get 1 there? That's not 1. All right, so this came from here, from f of 2x. If I plug in 1, f of 2 times 1, that should be 2. I screwed that up. So what is f of 2? Yeah, it didn't seem right. F of 2 is 0. Okay, great. So 0 times 1 times 1/2. Awesome. 0 minus 1/2 times -3 times f of -6. Well, what is f of -6? Okay, f of -6. It tells me this y value is -5. Minus 3/2. Okay, so 0 minus 1/2, or 1/2 times 3 times 5, so that would be 15/2. Negative, because I have an odd number of negatives, so there will still be a negative left over. Okay. Negative 15/2 minus 3/2. So negative 18/2, -9. All right, works out pretty nicely. So it's just practicing using integration by parts. Using areas of graphs. Okay, been working on that a little bit as well. Let's go to part D. The region R is the base of a solid whose cross sections perpendicular to the x-axis are square. Write, but do not evaluate, an integral expression that gives the volume of the solid. All right, so we're really focusing on this R right here. All right, cross sections. So this is Hayden's favorite. So what this means, we are looking down at R. We are birds flying over this graph. This graph is flat on the ground. R is the base. This is the bottom. And then coming up from R, so coming out of the screen, are squares. Weird thing to call me out for. You said last time you really liked this stuff. All right, so those squares are jumping out of the screen at us. Okay, so volume of cross-section seems much more complicated than it really is. It's just finding an area for the cross-section and then integrate that over the bounds. So write it over here. So what is the area of one of these squares? Well, what's the area of this side length? Right? Basically just asking what is the distance from here to here, which is just asking what is the y value. Right? From here to here is just whatever this y value is. Well, that y value is represented. This is a graph of f, so that's just f, right? That length is f. Okay, great. If that base length is f, then what is this side length? Well, it's a freaking square. So that's also f. All of these sides are f. So that area is just f squared. Okay, so to find volume, we just take area and integrate it over the interval. So where does this interval occur from? It goes from 2 to 5. So the volume equals the integral from 2 to 5 of f of x squared dx. That's it. Now it's a little easier because it told us not to evaluate it, but still. Hayden, did you go to your class yesterday with Miss Lee? All right, that's part E. So let's go to part E. Or no, wait, that was part D. Let's go to part E. For x greater than or equal to 5, the function f is not explicitly given, but f prime is negative 4, 1/2 to the power of x minus 5. If an equals f prime of n, find the infinite series from 5 to infinity of an, or show that the series diverges. Well, oh, RJ's here. Since when did RJ get here? Didn't even hit me with a good morning. Alright, that's cool. No problem, dude. No, that's fine. I'm not worried about it. Okay, so this information about like f prime, this is kind of more or less designed to just make you confused. That's not super necessary for us, if at all. Right? Because all we're trying to do is, all right, we're looking at this series of an. Well, what the heck is an? Well, an is f prime. Well, what is f prime? F prime is this. Okay, so really all we care about is making the link of, we are trying to find what is the infinite series from 5 to infinity of negative 4, 1/2 to the power of x minus 5, but instead of x, we'll do n. Right, because for series and sequences, we use n's. Waiting for the right time to say good morning. All right, cool. Well, we don't have much left, so. All right, so even though I'm told all this information that kind of makes it seem more complicated than it is, really I'm just trying to do this. Right? I'm just trying to do this series. I'm trying to show that I'm trying to either find the sum or show that it diverges. So this should automatically jump out at us as a certain type of series. Right? So I look at this and I immediately say, hey, this looks like a geometric series. Right? I have my a1 times the ratio to the power of n something. How do I know that an is f prime? Just, oh, I guess you can't see that. It tells me that. So I did no work to determine that. I just read the problem and it says, hey, AN is F prime. I said, great, no problem. I'll plug it in then. All right, but this looks like I recognize this as a geometric series. Okay, so for a geometric series, I need to look at, to see if it converges or diverges, I just need to look at what R is. So the ratio is 1/2. Absolute value of the ratio is less than 1. That's true, which means that this converges. If we had gotten some number that was greater than 1, or the absolute value is greater than 1 or equals 1, then it would diverge. But since this absolute value is less than 1, it converges. All right, well, if that's true, then we have a nice little formula we can use for the convergence of a geometric series, which is this. A1 over 1 minus R. So that's -4 over 1 minus 1/2. One minus 1/2 is 1/2. -4 divided by 1/2. So that's, I can think of as multiplying by the reciprocal. So the sum, the infinite sum of this series is -8. If we had found that our ratio was, the absolute value of the ratio was greater than 1, then we would just say the series diverges because it's geometric and the ratio, the absolute value of the ratio is greater than 1. All right, it's kind of like the geometric series test. But since we found that it converges, all right, the problem actually asks find the sum. So I wouldn't want to just stop at saying it converges, because the problem doesn't say determine if it converges or diverges. The problem says, like, if you can find the sum, then do it. All right, so the first part of that is showing that it converges at all, which means there is a sum. Well, what actually is it? That's where we use this neat little formula to determine. Right, so we find that it's -8. All right. Okay, so that's question 2. Wait, there's no more parts to that, is there? Is there an F? Okay, no. Go take Taylor and Maclaurin polynomials, the AFA. I saw, Reese, that you passed that yesterday. 10 out of 10. Well done. Amazing. Go take it. Go try it out. Make sure you... So I still need... We're coming down to got like 2 more days here that I need your responses on, specifically final answer on whether you're going to plan on taking the AP test or not. All right. Also, Reese, I saw your email. Going to respond to that. And again, let people know, please, if there's someone that you know that doesn't really keep up with the stream or is behind or whatever. Say, hey, make sure you respond to Mr. Abundis about the AP test. Okay, but I've gotten a handful of responses so far. And make sure, for those of you that are still taking it, which is everyone so far who's responded to me has told me that they are still taking it. So looks like you guys are still going for it. Cool. Again, I mean, why not? You've done all this work. Might as well try it out. The worst that can happen is you don't get college credit for it. But, oh well. Doesn't affect your grade in this class. Let's see, what else? Make sure you're studying formulas, practicing FRQ. Okay, previous ones we've done are the ones from the AFA. Practice them over and over and over and over again. Drill that information into your brain. Okay, even if you've already done an FRQ, if it's one that you know you've struggled with, great. Go do it again. Go do it again until it becomes just muscle memory of, oh, this type of problem, I know I need to do this. Right? Not just like for a specific problem, like, oh, okay, I know the answer is -3, so I'm just going to write -3. No. Practice the steps so you have the process in your brain. Right? I can vividly remember doing that so much in some of my harder college math classes. I specifically remember for one of my stats classes that I took it was like to get my master's. It's some of the hardest classes I've ever taken. Well, probably like the hardest classes. And one of them was a stats class. And we had to do these extremely hard problems that I just, like, I understood them, but could I sit down and do it on a test? I wasn't sure. And so I used to take all of our previous tests from the year, like going into the final exam. I took all of our previous tests from the semester, and I would just redo them. I'd do them over again. I'd redo it. And this professor gave us access to like the previous like 3 years worth of tests, because he would change the tests every year. So he would say, here's the tests that I gave last year, and here's the tests that I gave the year before that. So not only would I go back and do my semester's tests over and over again, I went back and did last year's tests over and over again. And I went back and did the tests 2 years before that over and over again, just to drill those steps into my mind of, okay, this is what I need to do. These are the formulas I need to use, so that when the final actually came for me, I was able to much quicker recognize, oh, this is this type of problem. I know that I need to use this process. All right, I spent hours, absolute hours, doing those same problems again and again. Right? Now, there's a lot of different problems, so it's kind of similar to you guys. You guys have access to, FRQs from going back like 4 years now on the AP test, or you have practice exams from like the past 2 years. Right? You have practice FRQs that we've done in class. Right? All of these. Don't just do them once and go, oh, that went well, or oh, that didn't do well. Drill the process. Okay, I know, I told you, I'm going to keep saying this stuff every day. Every day I'm going to keep saying this, because I hope you're doing it. All right. Okay. But I will see you back here tomorrow. I have a bunch of, AP just released a bunch of information and like a slideshow and a like video that I need to go specifically watch and take notes on to make sure I don't, miss anything. But so tomorrow will probably just be like an AP information day. So for those of you that are taking the AP test, or even if you're undecided yet, again, hopefully you're deciding soon though, make sure you're here or you watch the video, because I'm going to give out all the new information that AP has given to us. They just sent it out yesterday. So I just saw it this morning. So I'm going to go through that and see what it is I need to deliver to you guys. So make sure you check that out. Right. Otherwise, I will hope you have a great rest of your day, great Wednesday, and I'll see you tomorrow. Have fun.